Next, I want to talk about horizontal asymptotes. So it's a very similar idea to the vertical asymptote where you typically kind of see oftentimes like a split on the graph. But really what's happening there is that your values are going or approaching a certain y value. So instead of going to the x value where you see that kind of splitting towards infinity, it's the opposite idea. As you're heading out towards typically infinity or negative infinity, you're seeing that graph is leveling off toward a particular y value. So something like this, right? So as x is going towards positive infinity, that y value is approaching this b value. Same thing over here, right? You can look different ways. You can also go towards negative infinity as well. So you don't really have an example here, but it could be also going towards negative infinity. And we saw that in our original example. So in our original example here, you do have a horizontal asymptote at y equals 0. So at this side, you're approaching 0, and also on the negative infinity side, you're approaching 0. So sometimes you'll see asymptotes going one way, sometimes you'll see them going both ways. But the key thing is that as you go out to the infinities on the x-axis, you start to level off and approach one particular value. So we can see these on a graph. But again, it's good also to verify algebraically to make sure that you're actually seeing it correctly, right? Because it could be that maybe that graph is actually increasing slowly and you're just not noticing it. So it's good to always check algebraically as well. So let's say you have a rational expression. I know this is really confusing looking, but we're just saying you have some sort of rational expression. And what we really do is we focus on kind of that leading term in both the numerator and denominator polynomial. So n is the degree of the numerator and m we'll call the degree of the denominator. So if your n is less than m, so if the degree of the numerator is smaller than the degree of the denominator, then what happens is y equals 0 is always a horizontal asymptote. And that's what happened in our first example. So our example here was 1x, well, 1 over x. So the degree of the numerator was actually 0 because there was no variable there. And the degree here was just 1. So when the exponent in the denominator is bigger, you always have this horizontal asymptote of 0. If the two exponents are equal, so if the two degrees are equal, then what happens is you take the leading coefficients and you write them as a fraction. And that's what your horizontal asymptote is. And then the last one is if n is greater than m, then you actually have no horizontal asymptote. So let's see one of each type here. So for A, my numerator is 4x. So this has degree 1. And my denominator is 2x squared plus 1. This has degree 2, right? So the square is the highest power. Here, 1 would be my highest power. So what I'm noticing is my n is equal to 1 and my m is equal to 2. So my n is less than my m, right? 1 is smaller than 2. So when that happens, then y equals 0 is the horizontal asymptote. Okay. So when your bottom power is bigger, so that bottom power is bigger, then you always have a horizontal asymptote at 0. Now for the second one, notice that I have 4x squared for the top, so my degree there is 2. And on the bottom, I have 2x squared plus 1, so my degree there is also 2, right? I have squares. So my n equals 2 and my m equals 2. So what I have here is that they're the same. Well, when they're the same, then we take the ratio of the leading coefficients. So here it's going to be the 4 and the 2, and that is our y-intercept. So y equals 4 over 2, or y equals just 2, right? 4 divided by 2 is 2. Is the horizontal asymptote. So in this case, notice that my powers are basically the same on the top and the bottom, the leading power, right? That highest degree. In the last case, our numerator is 4x cubed, so you have degree of 3 there, and then we have that same 2x plus 1, so your degree is 2. So our n is 3 and our m is 2. Clearly, n is bigger than m. So when that happens, there is no horizontal asymptote. So in this case, the top is the bigger power. And those are the 3 things that can happen with horizontal asymptotes. Okay. Quickly, I think it'd be nice just to graph these. So let me show you maybe just 1 or 2 of them on Desmos. Let's see, stop share. So it is 4x divided by 2x squared plus 1. And I gotta zoom back out a bit here. Okay. So this was our first graph. This was A, and we said that y equals 0 was a horizontal asymptote. And you can see that here. You can see that the graph is approaching that y equals 0. Again, I'm going to change it to a dotted line just because it's actually not on the graph, right? But you can see that you're approaching that line y equals 0 in both directions. For an asymptote to exist, it doesn't have to go in both directions. As long as it goes at least one direction, it still counts. Part B, we had it like this. So what we did here is we changed the numerator to a square, and we had said that our horizontal asymptote was at 2 now. And you can see that. See how the graph changed? And now that those y values are approaching 2 as x goes to positive and negative infinity. And in the last example, we changed this to cube, and you can see here that there is no horizontal asymptote, right? You're kind of just going up in both directions. Each side is approaching positive or negative infinity here, so you're not leveling off to any y value. Okay. I also want to talk about one more thing in this video. I want to look and remind us about transformations. So remember that, we learned about transformations already, and we can apply those transformations to any kinds of functions. So I know we saw some other functions before, and now we're introducing 2 more. We're introducing the reciprocal function, which we just saw. And another common one is the reciprocal function, but being squared. So what happens here is you have the same, very similar idea where you're approaching 0 on one side and infinity up here. But this half basically kind of flips up here, because what's happening is that you're squaring everything, so all your outputs are going to be positive. It does increase quicker, so because you're squaring, instead of it just being 2 at 1/2, you're at 4 instead because you're squaring those values. But again, here you could find different values to plug in, like we did with the first example, in graph as well. So here I just figured I'd provide you the other graph, but if you want to try it at home, try different values to plug in, try plotting them yourself, and you should see that you do get this graph here. And you have a couple points as reference as well. Now, remember that we can apply transformations, again, to any functions. So now you can start doing that with these functions too. So if I go down here, I have the graph of my original function. So we're going to use the x1 over x squared function here. And then we want to graph this. So notice I have 2 changes, right? I have a +1 here. And I also have a -2. And I know it's been a while, but you want to remember that anytime you have addition or subtraction changes, these are always some kind of shift. So we're shifting the graph up, down, left, or right. These are the easiest ones. So we're not actually stretching it or squishing it or flipping it or anything like that in this particular example. Notice how the +1 is outside, right? It's an outside change. So this is going to be a vertical shift. And because it's a +1, we go up 1 unit. Notice how the -2 is inside parentheses, right? It's inside that square. So this is an inside change. And remember that inside changes are always horizontal. So this is a horizontal shift. And if it's a minus, you actually move to the right. So remember, inside changes kind of work opposite to what you think. Right 2 units. There we go. All right, so I'm going to draw the initial graph first, and I'm just going to redraw what's up here. So I'm just going to use some of those key points that they gave me. So that 1, 1, and then negative 1, 1. And then what do we have? 1/2, 4, and negative 1/2, 4. And then we have 2 and 1, 4. And negative 2 and 1, 4. So I'm just using those key points that they gave me from the graph here, the ones that were provided. And then I'm going to just fill in the rest of the picture. It looks something like this. Okay, so this is f of x. Notice here that you have that vertical asymptote at x equals 0, right? You have that splitting right at x equals 0, which makes sense. If you look at your denominator here, this is simplified and x cannot be 0, or that would make the denominator undefined, right? So you do have this vertical asymptote here. And then we also see that we have a horizontal asymptote at y equals 0. So if you look at that graph, you are going to continue off in both directions, kind of hugging that y equals 0 line or that axis. So for our new graph, we're going to shift it up 1 unit and also to the right 2. So each of these points, I'm just going to shift. So I'm going to go up 1 and right 2, up 1. Sorry, that should be right here. Up 1 and right 2. Up 1 and right. Oops, you know what? Let's do a different color because I'm making silly mistakes. Let's do green. I won't lie, it's a little hard to shift when your values are not on integers. So you want to be careful because like you just saw, I just made like 2 mistakes in a row with my counting. So you just want to be careful, right? These points here are at the halfway mark for the x values. So I just want to be a little bit more careful when I'm counting. So let me start with the ones on the axes first. So I'm going to go up 1 and over 2. So 1, 2. This one would be up 1 over 2. Here, we're going up 1 over 1, 2. Here, I'm going up 1 over 1, 2. Up 1 over 1, 2. Up 1 over 1, 2. Okay. So my graph is going to look like this. And this is going like this. This is going like this. All right, I apologize, a little bit messy. I'm going to show you the picture in the text too, so you can get a little bit nicer image here. But what's happening is because we're shifting, it's going to change our vertical asymptote, and it's also going to change our horizontal asymptote. So because we're shifting up 1 unit here, instead of having a, let me just write this in. So because we're shifting up 1 unit here, instead of having a horizontal asymptote at 0, you're actually going to have it up 1 unit at 1. And then here, because we're shifting to the right 2 units, again, instead of that vertical asymptote being at 0, it's now over at 2. So when you make those changes with your transformations, keep in mind your asymptotes as well. That's kind of a really good landmark for you, is that, you know, they're still there. So if you're starting at 0 and you're shifting 2 units to the right, now that vertical asymptote is over at 2. Or if you had a horizontal asymptote at 0 and you're going up 1 unit, that horizontal asymptote also shifts up 1 unit as well. And I'll show you the picture in your book because, like I said, it's a lot better than my drawing. And they do it in 3 different phases here. So they start with the original. Then they applied the horizontal shift first. So you can see that vertical asymptote went from 0 over to 2. And then they moved the graph up 1 unit. So that so your vertical asymptote is at 2, and now your horizontal asymptote bumps up to 1. So they also follow suit when you take on shifts.